Okay.
Hi everyone. Welcome to the seminar. So it's my pleasure to introduce Oindrila Ghosh, who's coming to us from virtually from Stockholm University, where she is a postdoc, having recently completed a PhD at the University of Hamburg. So she's worked on various topics from axions to other related topics to axions and dark matter and astrophysics. And today we're going to hear about some exciting new work to do with space plasma instability. So thank you for waking up early and giving us this seminar, and I'll leave it in your hands.
My pleasure. So thanks to Sharon and Sydney CPPC for this opportunity. So this talk is based on the three different projects that are connected by space plasma instabilities, which is the topic of this talk. So let me dive right into the very first one. Right. So the gamma ray sky, the extragalactic gamma ray sky, is full of TeV blazars. So these are essentially active galactic nuclei that have their emissions pointed directly towards us. And this could be typically flat spectrum radio quasars or BL-lac type objects. But for the purpose of this talk, I would focus primarily on these BL-lacs that peak at high energies, and they're characterized by hard power law spectrum. So from these blazars, from the TeV blazars, the TeV gamma ray emission, we observe for certain sources we observe these TeV emissions. But what we expect to see from these blazars are their corresponding cascaded GeV emissions. So how does that work? From a TeV blazar, when these TeV gamma rays, they meet the extragalactic background light, they pair produce, and the most abundant are the electrons and positrons. So they form a highly energetic pair beam. And these pair beams would propagate large cosmological distances well into the cosmic voids from the centers of galaxies. And in this process, the electrons and positrons in these pair beams, they would interact with the CMB photons and undergo inverse-Compton scattering, and therefore we expect to see this GeV cascade. So this is just standard model physics, and we would expect this sort of GeV bump here. However, we do not observe this, and this phenomenon has been quite ubiquitous for all TeV blazars that we have observed, this lack of GeV bump. So the natural question is either what is stealing these cascades, or is there something in between that's happening that we do not understand? So when neutral pair beams propagate through the intergalactic medium, it could undergo pair deflections with regard to the cosmic magnetic field, the intergalactic magnetic field, whose strength can vary from, say, 10 to the minus 17 or 18 to 10 to the minus 9 Gauss or so. So if such pair deflections take place, we could expect, for example, a pair halo. There could also be collective plasma effects that could lead to energy drainage from these pair beams into the background plasma of the intergalactic medium. However, if the intergalactic magnetic field is rather weak, then we could potentially have a scenario where the pair beam, the electron-positron pair beam, could undergo a broadening through magnetic diffusion. So I would get into the details of each of these phenomena a bit. So electromagnetic cascades. So the summary of the situation is electromagnetic cascades from pair productions on the extragalactic background light. This we know should be suppressed at low energies. Therefore, we expect to see a bump at higher energies, at GeV energies. But we don't observe this. And this tension seems to be a universal trend for blazars that we could observe, for example, through Fermi-LAT and MAGIC. And we want to understand why do we not see this GeV flux. So if we consider the scenario of pair deflection, meaning you have this pair beam and the intergalactic magnetic field is kicking the pairs away from the beam. If you have a strong enough intergalactic magnetic field, then these deflections could kick the pairs away from the beam, sufficiently far away from this beam. And the deflection angle one could express in terms of the magnetic field strength and the energy of the cosmic ray. And for smaller correlation lengths, this could be described by an RMS deflection angle. So this was the expression for a large-scale coherent field. And for smaller correlation lengths, the deflection angle depends on these variables. So the idea is if you have a strong enough field, it would kick the pairs away from the far away from this pair beam, and they would then cascade and contribute to, say, isotropic gamma ray background. However, if the deflection is not as strong, meaning the intergalactic magnetic field strength is not of the order of nanogauss, but rather of the order of, say, 10 to the power minus 11, minus 12 or so, then we could essentially have a pair halo forming around these pair beams, meaning the deflection is not strong enough to kick them far away. However, we haven't observed these pair halos. And another scenario is if the magnetic field, if the intergalactic magnetic field is even weaker, then this could introduce some diffusion in the beam. And this could, in turn, also turn off potential instabilities, the beam plasma instabilities that I would come to. So essentially, we see that these processes are coupled. So if the magnetic field is weak enough, it could introduce diffusion in the beam, which would stabilize the beam, because the beam is too broad to sustain the instability losses. However, if the magnetic field is at its closer to its lower limit that we have derived from, say, Fermi-LAT and MAGIC observations, then we start seeing that instability becomes more important. So how does the magnetic diffusion work? Say if you assume a two-dimensional Gaussian pair beam distribution at injection meaning when the pairs are being produced from the interaction between the TeV gamma rays and the EBL. So this is the Gaussian pair beam distribution, and the magnetic diffusion in the beam could be estimated in terms of the correlation length and the inverse-Compton characteristic length, and the strength of the intergalactic magnetic field, of course. Now, a year ago, this paper by Alavashra and Paul explored a Gaussian beam of this form, and they showed that the critical intergalactic magnetic field strength to win over the instabilities could be given by this purple line, which is obtained by setting the instability loss timescale to the inverse-Compton timescale. So the idea is they should at least be equal for instabilities to have an effect over inverse-Compton. It's for the instability to be more efficient than inverse-Compton scattering in draining the energy from the beam into the plasma. So in a recent analysis, we also looked at isotropic gamma ray background measurements. So far what we know is that local TeV blazars, the flux they have, that does not exhibit sharp spectral cutoffs at TeV energies. And we also know that the intergalactic magnetic field is quite weak. So it cannot efficiently cool the electron-positron pairs that are produced. And we also take into account that intergalactic, the isotropic gamma ray background is typically modeled with known sources, contributions from known sources, such as misaligned AGNs and star-forming galaxies or so. So this limits the diffuse blazar emission to less than 10%. And this is in quite strong tension with the blazar models. So with Tim Linden, Sunniva Jakobsen, and Carlos Blanco, we did this analysis where we looked at isotropic gamma ray background measurements, and we found that if the intrinsic cutoff for these blazars, they are above 6 TeV, then if you take into account the isotropic cascades and isotropic cascades from these blazar emissions, as well as the known blazar and as well as the known astrophysical sources contributing to the IGRB, the entire contribution, the total contribution seems to exceed the measured IGRB. So this in turn places a limit on how important instabilities could be versus how important the role of intergalactic magnetic field could be. So this introduces rather a sliding scale. So we could think of it this way. So if you have an intergalactic magnetic field that is sufficiently strong, meaning it's between pico and nanogauss strength, then you would have these isotropic emissions from their cascades, and this would then lead to an overproduction of the IGRB. Now, if we move to weaker intergalactic magnetic field, then we start seeing that if you don't consider a two-dimensional Gaussian beam for an example, as an example, but rather more realistic beam conditions such as Maxwell-Utner, or a more idealistic case, which is a monochromatic beam, meaning all electrons and positrons, the fresh pairs that are generated at exactly the same energy. So it's the same energy at injection. Then it seems that a much stronger intergalactic magnetic field could be required in order to win over the instabilities. So the instabilities could be, in other words, the instabilities could be, plasma instabilities could be important in a range between, say, 10 to the minus 18 to 10 to the minus 11 Gauss. This leaves a very broad range in magnetic field, and therefore it it motivates a study of beam plasma instabilities. So in the next part of the talk, I would dive into collective plasma effects and discuss how these plasma instabilities develop and what their implications are. So if you have any questions so far from this part, I would be happy to answer. All right, so moving on to the second part of this talk, which talks about plasma instabilities. So what are these plasma instabilities that are efficient whose efficiency we are considering in determining the energy loss from the beam into the background plasma? The instabilities occur when Langmuir oscillations undergo Cherenkov resonance, and these excitations, these resonant excitations, then transfer the beam energy into the background plasma. And they could be tracked, in particular, through the exponential growth of electromagnetic energy in the background plasma, or correspondingly the exponential decay of electromagnetic energy in the beam. So the dynamics and evolution of these interactions, they are typically set by characteristic length scales that are related to the plasma frequency. This is an important quantity to remember, because the rate at which the energy is drained from these pair beams into the background plasma depends on the growth rate of these instabilities, and they are typically of the order of the plasma frequency in question. So for intergalactic medium, the electron density here, that would give you the plasma frequency, is of the order of 10 to the minus 7 per cubic centimeter or so. So in order to understand how strong or weak these instabilities are, we need to look at their growth rates. So we can solve the dispersion relation. And as a first step, one can consider an electrostatic approximation, meaning we set the background magnetic field to 0, and we solve the dispersion relation for this electron-positron pair beams. So this would have this summation term. This has two different species. We would consider the beam electrons and positrons as one species, and the background plasma as a different species, even though they're both electrons and positrons. So the growth of the unstable modes could be described by this growth rate, which is the solution of this dispersion relation, and the imaginary part of the solution. So the key parameters that we see here that are crucial in determining the growth rate of these beam plasma instabilities are the Lorentz factor of the beam, which for astrophysical pair beams could go up to 10 to the power 6 or 10 to the power 7. The beam temperature, which is the width after the momentum width, described by the momentum width of the beam, meaning the dispersion in the momentum in a direction that's perpendicular to the direction of propagation of the beam. And the density contrast here means the ratio of the number densities of electrons between the pair beam and the background plasma. So these three parameters seem to be the most important while determining the growth rate and therefore the energy loss from these unstable modes. So when the wave vector is parallel to the propagation direction. These instabilities are often termed as a two-stream or Bunemann instabilities. And when they're perpendicular to one another, we have filamentation. And for every other situation, we have oblique modes, which is the most general case. And this is what we will consider from here on. So here you see essentially a 3D map of the growth rate, and the x and y axis correspond to the wave modes in the direction parallel to the propagation and perpendicular to the propagation. So for near monochromatic beams, which is an idealized scenario, you could have the instability growth proceed in the so-called reactive regime, which is when this condition is satisfied. And the growth rate looks like this. And this is taking into account a pair beam that could be, for example, potentially created in a laboratory setup with a density contrast much larger and a beam Lorentz factor much smaller. But we expect the same scaling relations to be valid. For beams that do not follow this relation, meaning that not all beam particles are injected at the same energy, meaning they have a finite momentum spread at the time of injection, then the growth occurs in the kinetic regime. And this essentially shows us that in this case, the growth is confined to a much smaller part of the momentum space. So the other phenomenon we expect here is beam relaxation, and in addition to heating of the background plasma, how the beam can heat itself, meaning how the beam can broaden, and the beam particles can undergo momentum dispersion. So both the instability associated energy losses and this quasi-linear relaxation of the beam could be expressed together in a closed form Fokker-Planck equation. And the diffusion tensor here in momentum space can be described in terms of the spectral energy density of these beams. And this delta function that appear here, and you have seen it before in the expression for the growth rate, this delta function is indicative of the Cherenkov resonance that leads to the growth of these unstable modes. Now, the spectral energy density in the background plasma grows exponentially, and the exponent is given by this imaginary part of the frequency, meaning this is the growth rate of the instabilities. And this constitutes the instability losses constitute this drift term. So this V here is P parallel dot, meaning this is the rate of change in momentum in the direction parallel to the propagation of the beam. And in another work with my Hamburg colleagues, I explored this Fokker-Planck evolution. I simulated a two-dimensional Gaussian pair beam and its time evolution, taking into account these instability losses as the drift term, and the diffusion coefficients could be described both in the parallel and the perpendicular direction in terms of this relation. So what we see is with regards to the time evolution of this beam, that the beam this is the momentum space of the beam. So even if you start with a very small dispersion at injection, eventually the beam becomes broad, which is very clear here. And also the beam loses energy. So the mean energy shifts to the left here. So this could be better seen here, for example. So I did this simulation for a density contrast of 10 to the power minus 3 in contrast to the astrophysical density contrast, which is of the order of 10 to the power minus 15, which is not realizable in a lab setting. And the corresponding gamma factor is 100 in contrast to, say, the astrophysical gamma factor, which is of the order of 10 to the power 6 or so. And I looked at how the mean momentum would change, and the change of the mean momentum, this is characterized by the drift, or in this case, the instability losses. They follow an exponential in time. And correspondingly, the standard deviation, here I show only the parallel direction. This would also grow exponentially. However, the exponents are different, as we would expect from a Fokker-Planck equation, that for the drift, this exponent has twice the growth rate of the instabilities, while the exponent in the diffusion coefficient corresponds to just the growth rate. So delta omega p. So delta is the growth rate in units of plasma frequency. And all of these calculations were performed in the linear regime, meaning we do not take into account nonlinear effects or mode-mode couplings. So in the next part, I would show which of these findings could be explored as well in a laboratory setting. So at DAISY, there's a proposed experiment where a high-powered laser goes through a plasma created in a laser wake field accelerator and hits a tungsten target. And this would then produce electron-positron pairs. And then you could use, for example, a magnetic field in order to guide these pairs so that they form a defined beam. And then we could pass them through plasma, which is essentially corresponding to the intergalactic medium, and these beams are those that correspond to the astrophysical pair beam, and we could see, for example, the signatures of these instabilities. Right. So we performed a particle-in-cell simulations, and we looked at the instability growth map, which looks very similar to what we would expect from a nearly monoenergetic beam. And the evolution of the energy budget in the beam plasma system, it shows that you are gradually draining energy from the beam into the background plasma. So in the ideal case, you would not have this green chunk, which is the field energy. So all of the energy from the beam should be ending up in the background, but this is not the case in peak simulations because of the limiting resolution of these simulations. So essentially, we also have this green component, and we also see this Fokker-Planck type of evolution where the beam is not only losing energy, but also it's broadening, in the sense that if you look at the mean momentum, it's shifted to the left, And if you look, this is in the parallel direction, where we would expect the impact of the energy losses to be the most prominent. And this is what we see. And in the direction perpendicular to the beam, we do not expect as much energy losses because the perpendicular momentum is not relativistic. It's mostly defined by the thermal dispersion of the beam particles. So here, again, the diffusion is the more pronounced effect. Right. So this is an evolution we see from particle in cell simulation. And the growth rate agrees with the reactive growth rate, the maximum reactive growth rate that we could expect, meaning the growth rate of a monochromatic pair beam. And these are the known scaling for such growth rates. We also notice that the extent of the energy loss of pair beams, they are sensitive to the gamma factor and the density contrast. In particular, for TeV blazar beams, we could see that this linear phase characterized by black dashed lines, as you go up in gamma, and as you go down in alpha, you start seeing a more prolonged linear phase, meaning that the instability growth will continue for a longer period of time if we are to extrapolate this in the astrophysical case, where the gamma factors of the order 10 or 6 or so, before it reaches saturation. And the saturation is brought about by nonlinear effects, which we cannot describe with perturbation theory, for example. Right, so we once again see the impact of the broadening and how it scales with different gamma factors and different density contrasts here. And we clearly see that this is quite pronounced for astrophysical pair beams. So the next natural question is whether we could observe this momentum diffusion in addition to the instability losses for cosmic pair beams. The answer comes from estimates from time delay observations. And if you look at the total time delay from magnetic deflection, inverse-Compton, and this instability-assisted broadening of the beam, you notice that for strong magnetic deflection, this term dominates over everything else. And if you go down further in the magnetic field strength, even then, for very weak magnetic field, the intergalactic magnetic field, say of the order of 10 to minus 16 Gauss and correlation length of 10 to minus 4 megaparsecs or so, which we would call in this case a weak tangled magnetic field. Even in that case, it leads the deflection and therefore the time delay, and it's about at least 100 times the contribution from pair beam broadening due to causal linear relaxation brought about by instabilities. Right, so this concludes this part regarding collective plasma effects. So if you have any questions up until this point, we could go over this.
Good. Now, just to clarify about this experiment, this is a new thing that you're proposing, because I guess people have studied plasmas for a while now. Is there not a sort of existing experimental data which you could exploit to understand these effects better, or is this something which really you need to do a dedicated experiment to try and understand?
Yeah, this is a proposed experiment, and this is something that would explore electrostatic instabilities. There have been some studies on other instability modes, such as Weibull modes, which are essentially generated by anisotropies in the plasma. So the anisotropies in the plasma drive up the magnetic field, and it grows exponentially. So that's Weibull instabilities, leading to filamentation structures in the momentum space. So those have been studied, but this experiment is particularly motivated by trying to understand what role electrostatic instabilities will play if you are to mimic this astrophysical pair beam in the laboratory. Yeah. So this is, as far as I know, first of its kind.
Okay, cool. Roland has his hand up. Do you want to go now, Roland?
Yeah, sorry, I'm afraid there's a lot I'm not understanding. Can you go back to the previous slide, please?
Mm-hmm.
So I guess I'm not, there's some basic picture that I'm not getting. Is it that you want the physically you want the pair beam from the blazars to be losing power into these instabilities, and so that you explain the fact that you have this missing energy at the GeV scale? Is that basically the idea?
Yeah, right. That's the idea.
So, all right, and I don't know whether maybe was this slide or the previous slide. It seems to be saturating. You seem to be saturating below 1, right? So that doesn't that mean that most of the instability is only taking it, say, most like 10% of the beam energy?
That's right. So instabilities are this is in the laboratory case, and the instabilities we see could take up to 0.1 or so, 10% of the beam energy. They are not extremely efficient at taking away the beam energy, if you are to think about it. But they compete with inverse-Compton scattering in terms of cascading, losing energy through cascades.
Okay, so I mean, but sort of to be blunt here, this shows that these cascades or these instabilities don't serve the purpose of explaining where the missing energy is going.
These instabilities cannot alone be the explanation. That much we have concluded from a laboratory perspective, but in the astrophysical case there could be other phenomena such as pair deflections, or even certain beyond the standard model processes, or certain standard model processes through which the cascade operates.
Okay, thanks for the clarification. Thanks.
Yeah. So essentially, if you are to explain the total energy budget, meaning if you want to account for all of the energy that is lost, instabilities alone cannot be the answer. And it depends, as I showed in the very first part of this talk, that for intergalactic magnetic fields that are very feeble, we see a competition between magnetic diffusion and the instabilities. Right. So in the next part, I will talk about what could be another observational probe of these instability losses. So let's recap a bit on how the instabilities lead to energy loss. So the energy loss, energy loss is exponential with regards to the growth rate of these instabilities. And the characteristic instability timescale is given by the inverse of these growth rates. So the initial spectral energy density, or the initial, you could say even the energy, is determined by the thermal fluctuation in the intergalactic medium plasma, so which is of the order of keV or so. And the maximum energy loss would be for a reactive case, which means you have monochromatic injection, and in the oblique growth, you have this scaling of alpha over gamma to the power 1/3. So if you have a single blazar, the intergalactic medium could be heated from the instability losses, because the instabilities are draining energy from the beam into the plasma, and this energy dump, in principle, could lead to a heating of the intergalactic medium. Now, for a single blazar, this is the spectrum of the blazar, this Fe, and this is the intrinsic spectrum, and this F is I don't show it here, but this is essentially a parameter that controls how much of the energy would be lost. How much of the energy is lost via instabilities as opposed to inverse-Compton scattering. So this is a parameter that tweaks the contributions in energy loss from inverse-Compton cascades versus the instabilities. And this is the pair production length. This is the mean free path of these photons. So this is the heating rate from one blazar, and this could be generalized to a population of blazars viewed in a certain solid angle. And you could essentially try to estimate the total heating rate from these blazars. Chang et al. In a paper from 2012 estimated this with a fit from 46 blazars, and it has this type of redshift dependence, in addition to a parameter that tells us how strong or weak the blazar heating is, consistent with the plasma instability growth rates. So I have excluded this strong heating that is discussed, for example, in this paper, because that's quite a very optimistic scenario. Instead, I consider from intermediate to low blazar heating. So the contribution of plasma instabilities here, they are contained in this term. So this tau plasma is the energy loss rate through instabilities, and this tau IC is the energy loss through standard inverse-Compton cascades. And the inverse-Compton loss rate depends on the energy density of the CMB, the Lorentz factor of the beam, and the Thomson cross-section. So if you compare the energy dependence, if you consider the redshift dependence of the ratio of these two losses, you see that the effect of these blazar heating is more pronounced at late times. So if we set, for example, z equals 3.5 as the end of reionization, we could try to model what would be the impact on the intergalactic medium through these instability-assisted heating. So in order to understand the total heating and cooling processes of the intergalactic medium, we need to take into account various heating and cooling terms that come from recombination, photoionization, photoheating, and Compton losses. And this I call here Q dot canonical. And the total uniform volumetric heating rate could be then the sum of this canonical heating terms plus this blazar heating term that we take from this fit from 46 blazars. Right, so now we want to solve the evolution, solve for this evolution of the temperature of the intergalactic medium. So we want to find the temperature density relation and temperature redshift relation. So the first term is the Hubble cooling, and this delta, this is the overdensity, and this sum of xi are typically called the atomic heating rates. So these constitutes all the processes that we talked about here. And this Q dot is the total volumetric heating rate. And then we solve this relation for a redshift between 3.5 and redshift of 2. And a typical solution, an ansatz for this type of equation could be envisaged as this relation. This is T0 is the temperature of the intergalactic medium at mean density, and this delta corresponds to the capital delta. So you could write, instead of 1 plus delta, you could just write capital delta here. And this gamma prime is essentially a redshift dependent index. So in the absence of blazar heating, meaning when you do not consider this QB dot term, when we solve this temperature density relation, then we have this type of scaling for gamma prime, and this is the temperature density relation for various redshifts, and this is the temperature redshift relation for various overdensities. So we noticed that the impact of heating is the most pronounced in the underdense regions, and this is observed from looking at different blazar heating scenarios. So here you see P equals 5.5, which corresponds to very low level of heating. In this case, the index versus redshift curve is inverted, and we start seeing the impact of this blazar heating in how these curves change. So this is again the temperature density relation for various redshift and temperature redshift relation for various overdensities. And in the underdense regions, which is characterized by this dark purple part here, the blazar heating is more pronounced at late times. And this is for a more optimistic heating scenario, which we call intermediate heating. And here this is even more clearly demonstrated that the temperature density relation has inverted, and we see the impact of blazar heating quite pronounced in underdense regions. So these estimates are consistent with Lyman alpha observations. So here we see a temperature redshift relation, for example, and this is between redshift 2 and 3. We compared this with our estimates, and they are consistent with also large-scale cosmological simulations for in absence of blazar heating, and in taking into account blazar heating, we derive a better fit. So after this, I moved to the final part of this talk, which is essentially the implication for small scale structure for these intergalactic medium heating. So since I'm quite short on time, I would not go through all the derivations for the filtering scale, but the gene scale and the corresponding filtering scale is modified through the sound speed from the intergalactic medium heating due to instabilities. And this could be considered as a baryonic feedback process, as it can flatten the dark matter density profiles and it can suppress subhalo formation, therefore posing as a resolution to the small scale crisis in cosmology. And especially if we look at, for example, void dwarf galaxies, which have the masses of 10 to the power 7 or 10 to 10 to the power 9 solar mass, the corresponding genes mass, the corresponding filtering masses that we obtain. This is a work I did with my master's student, Shankalan Bhattacharya, where we were looking at the genes masses and the filtering masses from these different scales of blazar heating, different degrees of blazar heating, and they seem to be consistent with these void dwarf galaxy masses. So in a sense, they compete, or they rather pose as an alternative resolution to the small scale crisis in cosmology, especially as a late time effect, and something that is the most prominent in underdense regions, because the dwarf galaxies cannot undergo, say, ram pressure stripping or tidal disruptions in these regions as easily. So they compete with, for example, wave dark matter or warm dark matter models as a baryonic feedback mechanism. And I would finish with things that I did not discuss here. So I considered the global blazar heating, which is supposedly uniform in all patches of the sky. However, this could be more refined using a patchy blazar heating formalism. Instead of a global volumetric heating rate, you essentially have a mean heating, and you add heating fluctuations, local heating fluctuations corresponding to the blazars, depending on their distribution. However, this has the limitation that they cannot be distinguished from AGN feedback models in certain cases. And also intergalactic medium could have inhomogeneities that could suppress the plasma instabilities corresponding to a length scale that is determined by the density. However, these inhomogeneities are fortunately not extremely strong in the intergalactic medium, and therefore the plasma instabilities could still play a significant role. So the key takeaways are, while propagating through intergalactic medium plasma, the pair beams can suffer from these instabilities that could be accessible through a narrow resonance window, in particular for kinetic regime, meaning non-monochromatic, more realistic beams with broad momentum dispersion at injection. However, the beams will continue to broaden in momentum space as a result, as a direct consequence of these instabilities. And therefore, this would lead to a quasi-linear relaxation of the beam, which once again would reduce the growth rate. And the instabilities can drain energy, as we have seen, from the beam into the background plasma, meaning from the AGN jets, the central black holes, into the intergalactic medium. And this could alter the thermal histories locally. In case there is not a significant inhomogeneity in the intergalactic medium, and the intergalactic magnetic field strength is feeble, then the GeV-TeV tension could be resolved, taking into account the magnetic deflection as well as the plasma instabilities, in order to account for these missing GeV bumps. So if you have any questions, I would be happy to answer. Thanks.
Thank you very much. Yeah, I mean, I know some people will have to go, but do we have any quick questions before we do? If not, I'll begin. I would just, yeah, this is going back quite a way, but I'd like to get a better appreciation for how significant this tension is on the side of the data. I mean, you mentioned that this is basically all the blazars exhibit this tension, but I mean, is this how many blazars are we talking about here? Is this like a very large population of these things, or is these are quite rare objects, or so I guess, is there anything on the side of the data that can help, you know, maybe if you just had more of them, more things would reveal themselves?
Yeah, I don't have the exact number, but I think it was of the order of close to 100 blazars. A few years ago, it was, I think, about 82 blazars or so, and now we have data from even more blazars, and they seem to solidify this tension, that it's quite omnipresent.
Yeah, and this is primarily coming from like ground-based Cherenkov telescopes, right? This
also for Milan.
And for, yeah, right. But I guess in terms of the future, is this I mean, this CTA will improve the situation in some way, or?
Yeah, I mean, one could expect. I mean, the most recent limits come from MAGIC, and we could expect definitely better resolution from CTA.
I'd also like to ask, this is sort of going a bit off topic from what you discussed, but I remember I think in this original paper you had, you did sort of speculate on the possible implications for axion-like particles, like axion-like particle oscillations in the magnetic fields. Is there given what everything you've said, do you think it's premature to be entertaining those kind of options, or do you think this is there could possibly be an effect here coming from some axion?
Yeah, so we are currently exploring this aspect here in Stockholm for in particular for axions that are not ultralight, whether they could essentially drain some of the energy through different processes. Yeah, but it's still at a very preliminary state, so I can't comment very conclusively yet. But this is a very interesting direction to look at, certainly.
Cool. All right, last chance. No, I think we're relatively earlier, unfortunately. But yeah, thank you, everyone.